Okay, so usually this is the problem of like you come up with hypothesis about something, for example, the population mean. Okay, you conjecture that it equal to a certain value, and then you will try to find some evidence to support your claim, right, about something, for example, about the population mean. So you're trying to find evidence to support your claim. The evidence in this case is the data you collected, right? So usually there are two conclusions for hypothesis testing. You may end up rejecting the null hypothesis, or do not reject the null hypothesis. Okay, one of the two conclusion, one of the two possibility. But once you know that, once you conclude that the null hypothesis should be rejected, it does not mean your conclusion is true, right? It doesn't mean like that, but it means that based on your data, you have enough evidence to say so, right? To conclude that. But in reality, your conclusion may be false. Okay, so that is refer to the error of the test, right? Okay. So for example, so far we have something like this. Okay, you may say, okay, the mu is different from this, right? The mean, okay, the mean is different from 24,672 US dollar. Okay, what does that mean? Okay, the average cost of rehabilitation of stroke victims. Okay, so you claim that in average the cost of rehabilitation for the stroke victim is different from this. That is your claim. And then in order to support your claim, you may like collect some data, okay? Because your claim is about the population, right? Any rehabilitation must be included, okay? And if you know that, you can compute the real mean, the real average value. But in practice, it's impossible because you not always approach the population data. That's why in practice, you have just resort to collecting a sample, right? Selecting a sample. So in this case, we're trying to find a sample to support whether our claim should be rejected or is right or not, right? So the conclusion may be end up with whether you have this or this, right? But again, since nu is unknown, so when you come up with the conclusion, you cannot say it is true or not, but at least you can just say you have enough information to conclude or to say so, right? To say so. But it may happen that your conclusion is incorrect, right? Incorrect. That's why in hypothesis testing, there are two possibility of error. Okay, we have type 1 error and type 2 error. Type 1 error is, okay, let's review a little bit here. Okay, this is just your claim, right? And claim. Okay, so we do, have two kind of hypothesis, H0, and we call this null hypothesis, and H1 is the alternative hypothesis. So you may come up with like reject X0, and in that case, okay, just like look at this, maybe it's more convenient to explain why using this. Okay, suppose that this is one hypothesis, okay, and this is the now I'm sorry, the alternative hypothesis. So as you can see, we have two kind of error. Okay. The type 1 error is that you reject the null hypothesis while it is true, right? It means that in reality, H0 is true, but based on your data collected, you conclude that H0 is not true, or you reject it, right? You reject it. So that is one possible error, right? Yes. So here, suppose that the null hypothesis is true, which means that you are not pregnant, and then you come up with rejection it, right? Reject it, right? So you reject this, it means that you are not pregnant, it means that you are pregnant. But of course, this is your claim, or the original claim, and in reality, this guy is not pregnant. It's true because he is a male, right? But you come up with a conclusion that this guy is pregnant. That is possible error. And another error is that you do not reject null zero, null hypothesis, when it is false. Okay, when it is false. So here, if null hypothesis is false, it means that the in reality the guy is pregnant, right? The guy is pregnant, but you do not reject it, right? You do not reject it. It means that you say that you are not pregnant, but in reality it is true that this woman is pregnant, but you come up with conclusion that you are not pregnant. So this is the two possible error in hypothesis testing. Okay, and so far we have deal with hypothesis related to this population mean, right? You just come up with a claim, and then you're trying to find evidence to support your claim, right? Okay, and eventually you come up with two possibilities in your conclusion, right? Whether the null hypothesis should be rejected. Okay, and in this lecture, we move to another thing. Okay, we move to another thing. It is about the test with a population proportion. Okay, but I will not consider this. I just move to the test for a variance or standard deviation. Okay, this is makes sense because in general, the two parameters, the population mean and the population variance are unknown, right? So you may also want to test about the variance, right? Originally you test with the mean, now just move to another step. You want also to test the variance. You come up with a claim with related to the variance, and then you're trying to collect data, and based on that data you may come up with conclusion whether your claim is true or not, right? Okay, but in this case we have to assume that the population is normally distributed, right? Okay, I'm sorry, I'm trying to erase this, but I don't have time. That's why this is just a typo. Okay, there should be no this phrase. Okay, so we just assume that we just select a sample of cyan from a population whose distribution is normal, right? Yes, we assume that the population is normally distributed, and then the two parameters are unknown, and then you try to come up with some hypothesis related to the sigma square, the variance. Okay, the null hypothesis could be like, you may say, okay, the population variance equal to a certain value. Okay, this is our initial hypothesis, right? It means that the variance is equal to a certain value. This is mean a certain value. You can denote this by any other letter, okay? But make sure that this is a certain value, right? It means that the null hypothesis claims the variance equal to a certain value. And the test hypothesis, the statistics, the test statistic in this test a little bit different from the mean test. So you have to work with this kind of test, right? You have to work with the sample variance x square, and this is the n-1, n is the sample size, okay, and sigma 0 square is the certain value, okay? So you have to test, your test statistic is this, right? And we call it chi-square because, as you know, when you study confidence interval related to the variance, it related to the chi-square distribution. When we're working with confidence interval with the mean, we're working with the standard normal distribution or the t distribution. But when we move to the confidence interval for the standard deviation as well as the variance, we will involve with a different distribution called the chi-square, right? And at that time we denote it by this letter. Actually, this is chi-square. This is the Greek letter called chi, right? Chi-square. So this is three possibility of the alternative hypothesis. Okay, this is the original hypothesis. I mean the initial hypothesis. So you may have the one-tailed test. Okay, one-tailed test. You may have another hypothesis as that the true value of the variance is strictly greater than this certain value, or it's strictly less than, right? These two tests is the one-tailed test, right? Or you may have a two-tailed test, like the null hypothesis in this case is that the variance is different from the original value. And this is the corresponding rejection region for the three tests. Okay, so in this case, the rejection region is you have to look at any value that greater than this, right? Okay, you already see something like this when we working in the confidence interval. At that time, we call the right. Okay, just a moment. Here, okay, here we have Okay, x. Okay, x chi-square left and chi-square right. That is what it means, right? By that because like t distribution, chi-square distribution is characterized by the degree of freedom, right? The degree of freedom. And unlike the t test, the t distribution, chi-square is not symmetric, right? This is one example of the chi-square curve, and then you have to also working with the critical value, right? You come up with a critical value. You may say chi-square right correspond to like this value, right? This means that this is the point at which the area under the curve to the right is alpha over 2. So and this is the left when you think of the area to the left. This is when you think of to the right. But this is a different notation. Okay, a different notation. Okay, this is just the same thing, right? N minus 1 is the degree of freedom of the chi-square test, and this alpha, okay, this alpha is the what is mean? Okay, it is the significant level, right? Significant level. So when you have only this is the right test or the upper test, right? Upper tail test. So what does it mean? This means this one, right? Instead of call it chi-square right, in this case I just call it chi-square alpha n minus 1. N is the degree of freedom, because you may have a lot of chi-square curve when you just specify the degree of freedom. This is several chi-square curve correspond to 4 different degree of freedom, right? And the way we define the critical value is in this way. Okay, chi-square right here in this case mean in this one. It means that this is the point that the area to the right is alpha, right? It's alpha, and you have to specify the degree of freedom n minus 1. And for this, this is actually the chi-square left, right? Because for example, if I say that this is alpha, this must be chi-square alpha, right? If this area is alpha, this is chi-square alpha. But in this figure, this area is alpha over 2. So this is chi-square alpha over 2, right? So to come up with this value, you just take alpha to be, okay, 1 minus alpha. Why? Because if this is alpha, 1 minus alpha means the area here is 1 minus alpha, and the area here is just only alpha. So we mean, okay, this is just the right, the left chi, the left chi left, right? I mean the left chi-square value. And this is the case when we think of two tail, right? Or both tail. So when you specify the significant level alpha, you have to set the area to the left and to the right alpha over 2, right? So what is the corresponding chi-square right? It is this one, right? It is this one, chi-square alpha over 2. This is exactly chi-square right, and the chi-square left in this case is exactly this one, right? Because when you want it to be here, the chi-square, this area must be 1 minus alpha over 2 to the right, right? To the right. area to the right is 1 minus alpha over 2. Okay, this white area is 1 minus alpha, but when you plus this more, you're gonna have 1 minus alpha over 2. That's why here it is chi-square 1 minus alpha over 2, and you have to specify the same the same degree of freedom, right? If you look at this, everything just quite similar to the case of test for the mean, except that we switch from we switch from the standard normal distribution or the t distribution to the chi-square distribution, right? To the chi-square distribution, and everything just works in the same way. Okay, this is nothing but the critical value, right? This is the critical value here. Chi-square right or chi-square left, we mention it as the critical value, right? Just like for the z, for the case of standard normal curve or the t. Okay, where is that? Just okay, here. Okay, this is correspond to the standard normal curve. Okay, and it is the z curve, and the distribution is z, right? Standard normal, and the corresponding critical value we denote it by z alpha or z alpha over 2. And similarly, for the t curve or the t distribution, the critical value we denote it by t alpha. Alpha here, it just means the same way as the significant level, but t here you have to index it by two values, the significant level alpha and the nu, which is the degree of freedom. And similarly, in the case of chi-square, everything just works the same. Okay, everything just works the same. Okay, this is a chi-square curve, right? Because the distribution is the chi-square is chi-square, right? And this is the corresponding critical value. But since the curve is no longer symmetric, that's why you have to say two different things, right? Chi-square right and chi-square left when it's come up with the two-tailed test. And it is nothing but here, right? It's here. Okay, so let's move to the point. The point is that an instructor wishes to example. This is example. An instructor wishes to see whether a variation in score of a. Okay, maybe it's better to have an example here. Okay, I'm sorry if it is raining now. That's why you may hear some noise from the outside. Okay. Okay, so this is one example of the hypothesis testing for variance. Okay, so IQ test. A psychologist wishes to see if the variance in IQ of 10 of her counseling patients is less than the variance of the population, which is this. Okay, the variance of the IQ of her patient is okay. Please Please let me know if you can hear me clearly.
Yeah, I can hear you clearly, Professor.
Okay, because
Yes,
I
sir.
read because I myself just hear the noise very noisy, and okay, it's okay if you can see clearly. If you can hear clearly, okay. So this is how we can use the chi-square test. Okay, uh, so the variant of the IQ of her 10 patient was, okay, this is the variant. Actually, this is the sample variance. Okay, this is actually the sample variant because this is based on the sample. You select a sample of 10 patients, right? Yes. Your claim is we're trying to compare the variant of the IQ of the patient selected to the variant of the population. So we know the population variant is this. Okay. So in this case, you have to state this hypothesis that this is your null hypothesis is okay, original claim. Okay. And your claim, this psychologist claim is that the variance is less than this, right? It's less than this. So first of all, we have to find the critical value. Okay, the critical value. Since this is the left tail test, why it is left tail? Because here you have to. It depends on your alternative hypothesis, right? If the sigma square is greater than a certain value, it is considered as the right tail test or the upper tail test. And when it is less than certain value, it is the left tail test or the lower tail test. And if it is different from a certain value, it's considered as the two-tailed test. We classify this exactly the same as the case of the population mean test, right? But since the alternative in this case is less than a certain value, it is the left tail test. And we want the significant level of 0.05, which means that we want the, okay, if you think of confidence interval, the confidence level is 95%, right? 95%, which corresponds to the significant level of 0.05. Okay, so so when your alpha is 0.5, 1 minus alpha is 0.95. And the degree of freedom in this case equal to the total, the sample size minus 1. Sample size in our case is 10 because we select a patient of 10, right? So the degree of freedom in this case is 9. And the critical value is this. Okay, why is that? Because here we want the left. We want the left test, okay, left tail test, this one. Then this is the critical value, okay. Chi-square 1 minus alpha, right? Because we want actually we want this area, okay. We want this area to be alpha, okay, to the left, right? This area to be alpha, and then the area to the right is 1 minus alpha. That's why in this case we need 1 minus alpha is 0.05, and then this is actually z chi-square, okay, chi-square 0.959, right? because 1 minus alpha is 0.95 and the degree of freedom in this case is 9, right? Okay. And then this is your test value. Okay, your test value. You have to compute this n minus 1 times sample variance divided by the second value. That's why you have to compute this. Okay, n minus 1, 10 minus 1, and s square. We know that it is given. Okay, it is given. Oh, I'm sorry. Here it is given. It is given, and divided by the original value, right? The original value, and then you come up with this. And then how to make conclusion? Okay, here you can make. You can see the maybe it's better look. You want this area to be 0.05, right? You want this area to be 0.05, and then you want to identify this point, right? So how to get this value? You have to look at the chi-square table. But the chi-square table just gives you the area to the right. So if you want this area to be 0.05, the area to the right must be 0.95, right? So that's why we have to compute this 0.05 and specify the degree of freedom. You can come up with this critical value. It's mean get this value, right? And then you have to compute the test value. In this case is 8.24. And how you decide? Okay, how you decide? For the left tail test, okay, because our problem is left tail test, the corresponding rejection region is this. You have to compute the test value. If it's less than this critical value, it means that you have to reject, right, the null hypothesis. But if, in contrast, if it's greater than this value, you have to do not reject, right? Do not reject. So that's why when this is the critical value and this is the test value, and as you can see, this is the rejection region, but now the value is outside the rejection region. That's why you do not reject, right? Do not reject the null hypothesis. Okay? Do not reject the null hypothesis because our test value fall outside the rejection region. This is the rejection region. If the value is less than this, you have to reject the null hypothesis. But in our case, the test value is 8.04. It is to the left of this value, which is outside the rejection region. That's why you have to come up with this conclusion. Do not reject the null hypothesis. And how can you say? How can you summarize your result? There is not enough evidence to support the claim that the variance of her 10 patients is less than this. There is no enough evidence to reject this null hypothesis, or equivalently, there is no enough evidence to support this, right? Okay, again, we come up with a conclusion of do not reject the null hypothesis. It means that there is no enough evidence to reject this, or there is no enough evidence to support this, right? There's no enough evidence to support this. So we don't have enough evidence to support the claim, right? The claim of what? The claim of alternative hypothesis. Okay, this is another example. Okay, it's about outpatient surgery. Okay, a hospital And Mr. believes that the standard deviation of the number of people using outpatient surgery per day is greater than 8, right? The standard deviation is greater than 8. A random sample of 15 days is selected and the data is shown. Okay. What is that? Number of people using outpatient surgery. Okay, outpatient surgery ជាការវះកាត់ឲ្យចេញទៅក្រៅអត់សម្រាប់ទេអញ្ចឹងមានន័យថាគាត់រើស15ថ្ងៃមកសិក្សាថ្ងៃ okay one day there are 25 outpatient, okay, using there are 25 patients who use the outpatient surgery in this specific day, and there are 30 patients using the service in another day, and so on. And then we want to come up with a significant level of 0.10. So we want to know if there is enough evidence to support the administrator claim. How he claimed? He claimed that the standard deviation of the number of people using the outpatient surgery per day is greater than this, right? So you may come up with this hypothesis and identify the claim, right? So this is the null hypothesis. It compare with 8, right? So this is the certain value of standard deviation, and because the claim is that it greater than, okay, this is the claim of the administrator. So in this case, the claim of the administrator is alternative hypothesis. So since the standard deviation is given, it should be squared to get the variance. Okay, so first of all, again, we have to compute the critical value correspond to this significant level, right? We want a significant level of 0.10, and you also have to specify the degree of freedom. So the degree of freedom is 14 because we select a data of 15 days, right? So the degree of freedom in this case is 14, and the test is right test or upper test. I'm sorry, right tail test or upper tail test, because the alternative hypothesis is greater than, right? It's greater than. So in this case, you come up with this critical value from the table. Okay, we want this area to be 0.10. So the critical value in this case is 21.064. Okay, here. And how to come up with this value? You have to look at the chi-square table, because I already tell you how to do that when we working on confidence interval for the variance as well as for the standard deviation. And another way of come up with this value is using R, right? You have to use the right command to come up with this value. And again, you have to compute the test value. Okay, this is still our test value. Even we come up with a test related to the standard deviation, not the variance, but the test value still working with the variance. But again, since the standard deviation is given, you just square it, you come up with the variance. That's why everything is realized here. So just replace. Okay, n is 15 because we select a sample of 15, and s square is 11.2 square. Okay, how to come up with 11.2? Because this is a sample, if you compute the sample variance, you will obtain this, right? 11.2 square. This is the sample standard deviation, 11.2, based on this data. Okay. and 64 is a square of 8, right? Because the sigma is originally claimed to be 8, right? So this is a test value, and in this case the test value is to the right of the critical value, and this area is the rejection area, and our test value based on the data, based on the sample, it is inside the rejection region. That's why the data suggests us to reject the null hypothesis, right? So the decision is to reject the null hypothesis, right? Because the test value is greater than the critical value, right? Or in other words, it falls inside the rejection region or the critical region, because this region is called critical region or rejection region, just the same thing, synonym. And the result is there is enough evidence to reject null hypothesis, or in other words, there is enough evidence to support the alternative hypothesis, which is the claim of the administrator, right? So that's why we come up with there is enough evidence to support the claim that the standard deviation is greater than 8, right? Greater than 8. Okay, and this is an example of a two-tailed test. Okay, we want to think it's related to the nicotine content of cigarettes. Okay, a cigarette manufacturer wishes to test the claim that the variant of the nicotine content in its cigarette is this value. Yeah. Nicotine content is measured in milligrams and assume that it's normally distributed. So a random sample of 20 cigarettes has been selected, and we measure that the standard deviation is 1 milligram. Right? This is the sample standard deviation because this value is calculated from this sample. Okay, this sample. And we want the significant level to be 0.05. So the question is that, is there enough evidence to reject the manufacturer claim? Okay. We claim that the nicotine content just only this, right? So based on because maybe according to the law they have to restrict a certain variance, right, of the nicotine inside cigarettes. So in order to see whether this kind of cigarette observe the law, we have to test this value. So based on what is told, you have to state the hypothesis and identify the claim. Okay, this is a claim because he claimed that the variant is, okay, this value, and this is the alternative, right? The alternative. So again, in this case, because the alternative is different, it is the two-tailed test, right? Two-tailed test. Okay, so you have to set 0. Okay, alpha is 0.05, so you have to divide alpha into 2, 0.025, and another 0.025 to the left, right? So what you have to do is to compute this critical value corresponding to this. Okay, so again, using this critical value and this degree of freedom of 19, because we have a sample of 20 cigarettes, the sample size 20, the degree of freedom in this case is 19, and using this significant level for the two-tailed test, we come up with this critical value, right? So in this case, the rejection region is to this or this, right? So you have to compute the test value. Okay, you have to compute the test value using the same test statistic because everything is given here, right? And then you come up with a test value of 29.5. And again, where is 29? 29 is between this critical value. So it's outside the critical region or the rejection region. If our test value is inside this or inside this region, we have to reject the null hypothesis. But it's outside. It's outside. Do not reject. So the conclusion is that do not reject the null hypothesis since the test value just fall between the critical value, or in other words, it's stay outside the rejection region. Right? So this is how we conclude. Right? There is not enough evidence to reject the manufacturer claim that the variant of the nicotine content of the cigarette is equal to this value. Okay, and this is finish what I planned for you. Actually, you may ask like, okay, the way to conclude the hypothesis testing can be look at or compare the test value with the critical value, right? As you have seen so far. And another way to come up with the conclusion, you may compute the p-value instead, right? And then compare the p-value to the critical value. That is another way of doing that. But since you have seen this in the case of hypothesis testing for the mean, it works just exactly the same way for the hypothesis test for hypothesis testing for the variance as well as the standard deviation. So I think it's good enough to finish here. Okay, to finish here. So please let me know if you have any question.